Assalamu alaikum. Hope everyone is good. Yesterday, what we did, we saw what is a symmetrical fault and how it can be solved. Let us try to do some numericals on the same topic. This is actually a PDF of a book, Power System Analysis, in which the question reads like this: a synchronous generator and a synchronous motor each are rated 20 MVA, 12.66 kV, having 15% subtransient reactance are connected through the transformer and a transmission line as shown in the figure. The figure is like this. This is the figure. We have a generator, a motor, transformer, step down transformer, step up transformer, and a transmission line. We can see that this is the sending end and this is the receiving end and this is the transmission line. So the transformer rated at 20 MVA, 12.66 by 66 kV and 66 by 12.66 kV with a leakage reactance of 10%. The line has a reactance of 8% on 20 MV 66 kV. The motor is drawing 10 megawatt at 0.8 leading power factor and a terminal voltage of 11 kV when a symmetrical three-phase fault occurs at the motor terminals. Determine the generator and the motor terminals. Determine the generator and the motor current. Also determine the fault current. So this is the system. Its voltage is 12.66 kV. And it is stepped up by this transformer as its voltage ratio is 12.66 to 66. So the line voltage over here is 66 kV, and here the transformer ratio is 66 by 12.66. But here the voltage is given to be 11 kV, and power is given to be 10 megawatt. So we'll first choose the base value for power and the base value for voltage. The base value for power can be taken this 20 MV. It becomes quite easy. You don't have to change the value of reactance, different reactants, because all the reactants are given on the same base. 20 MV and 12.66 kV on generator side. This side. So on this side, it will be 20 MV, 12.66. That means on this side the base kV will be 66 kV, and on this side the base kV will be 12.66 kV. This is the base kV. Actual voltage is 11 kV. That's something different. We need to convert it into per unit. So all the reactants given on the base turn are an appropriate voltage. We don't have to change them because they are given on the same rating. So here we don't have to change them. First we will calculate V0. V0 is the voltage at this bus, that is the terminals of the motor. Since it is given as 11 kV, our base is 12.66. It comes out to be 0.8688 at an angle of 0 point. We can take this as a reference. It is reactance diagram. You can see that this is converted to EG and reactance. This is the reactance of the transformer T1. This is the reactance of the transmission line. This is the reactance of the transformer T2, and this is the reactance of motor and its back EMF EM double dash. So double dash means the subtransient part that we have discussed in the last class. So load is 10 megawatt, 0.8 power factor leading. That is, load is 10 divided by 20, since 20 MVA is its base. So it comes out to be 0.5 per unit. You might be wondering that it is MVA and this is megawatt, and I have told you their unit should be same. Since I told you in this beginning class in which we have discussed the per unit system that this comprises of all powers, whether it is reactive power, whether it is active power, whether it is complex power, whether it is apparent power. Whatever is the base is this, that is applied to all these powers, and dimensionally they are equal. Dimensionally their dimensions are equal. MVA, MVAR, this complex power or megawatt, dimensionally they are equal. That's why this also comes out to be unitless. So what will be the I0? I0 will be equal to voltage divided by power divided by voltage divided by power factor, and it comes out to be equal to 0.719194 at an angle of 36.86, because here it will be plus sign because the current is leading. This is actually I0, that is current flowing through this circuit before the fault occurs. Before this there is no fault. We are not considering any fault. Now These are the different reactances. This is the reactance of transformer, reactance of the transformer, reactance of the line. So usually the reactance of the line is not, I don't know whether it's given on this. Yes, it is also given in per unit percentage. You can convert it into per unit. It comes out to be 0.08. So the reduced circuit will be like this, because 0.1 plus 0.1 plus 0.1 is equal to 0.2 plus 0.8 is 0.28. That is written over here. This is equivalent reactance. 0.15 is kept there and 0.55 is kept there. Now when this is short circuited to this point, the equivalent circuit becomes like this. It is connected to this. So we need to calculate Ig double dash, we need to calculate Im double dash, we need to calculate If. You can see from here, this Ig double dash plus Im double dash will be equal to If. So here we can calculate this from figure 8.2, voltage behind subtrans reactance, that is this Eg dash. It will be equal to this voltage. Sorry, Eg double dash will be equal to this voltage plus the voltage drop of these. That is V0 plus this I0 into this reactance totally. That's 0.28 plus 0.15. That will be 0.43, like this. That is 0.43. That is, this will be the voltage at the bus, and this is the voltage drop of this. This is the current. This is the total impedance. It comes out to be 0.7266, 19.9 degrees tolerated. Similarly, Em double dash, that is the voltage at this. This is the voltage before the fault occurs. It comes out to be equal to this voltage minus voltage drop of this, because the current direction is from Eg to this. So this voltage drop minus this, this voltage V0 minus the voltage drop across 0.15. So that's why what is given over here, this is the 0.15 multiplied by its current, this is the voltage drop. It comes out to be 0.9375 minus 5.28 per unit. So this is also quite exact result, because power flows from leading angle to lagging angle. So this is 0, this has to be some negative angle. Since power flows from here to here, if it is 0, this has to be positive angle. And the angles come as per the power flow. You can see 19.9 positive with respect to this, and this 0 is positive with respect to this. So from figure 8.3, what is Ig double dash? This Ig double dash will be equal to Eg dash divided by this impedance, because this impedance will not be there. You can see when this is when we use a superposition principle, we short circuit this, there will be no current flowing through this. All the current because of this will flow through this. So in that case, this Ig double dash will be equal to Eg double dash divided by these impedances. That will be equal to Eg double dash divided by J 0.43. That is given over here. You can see Eg double dash divided by J 0.43. It comes out to be this value. So Im double dash will be equal to Im double dash will be equal to Em double dash divided by J 0.15. Im double dash is here, J 0.15. It comes out to be 6.25. This angle. So fault current will be the summation of two, which we have discussed earlier. It comes out to be equal to minus J 7.88 amperes. So finally, we'll calculate all the currents in the actual value. These are the per unit values of the fault current. So base current will be equal to MVA, that is the per phase current, MVA divided by root 3 divided by this, that is 912.0.25, 0.85. So Ig dash multiplied by this is coming out to be 1540.5. This angle will remain the same. Im double dash will be 5700 this, and If will be equal to total current. So this is how we can calculate the fault current, or we can say this is the fault analysis. We do the fault analysis of any circuit by using the per unit value, and fault analysis is always done by using this per unit values. I hope you understood this. Let us come to one more. Let's come to one more numerical. A radial power system is shown in a network like this. This is a radial power system. Radial means when the generator station is at one end, and from that end to the load there is no generating station in between, and continuously up to the load end there are only the load points. There are no generating point like this. Here we have the generating stations at the 2 points, and then we have a radial network, and in between them there are no generating stations. So such type of network is called a radial network. A three-phase balance fault occurs at the F. That means three-phase balance fault occurs at this point F. Determine the fault current and the line voltage at 11 11.8 kV bus under the fault condition. We need to find out the fault current. 11.8 kV bus is this. We need to find out the fault current, that is the current flowing from this point to the ground, and what fault current, line voltage, and the voltage at this bus, and we need to calculate the voltage at this bus. The rating of the generators or transformers are given in the figure itself. You can see its rating is 12 MVA, XD1 is 0.12, XD2 is 0.15, its MVA rating is again 12 MVA, and the bus is 11.8 kV. It means the ratings of the generators are also 11.8 kV. So here, this is 12 MVA, transformer is 12 MVA rating, and when it's not given what is the value of its voltage ratio, we can take the voltage ratio 11.8 in this bus and 33 kV on this bus. So its line impedance is given as 9.45 plus J12.6 ohms. It is to be converted to current value. And then transformer T2, it means its transformer ratio is 33 by 6.6 kV, and it is 3 MVA, and its reactance is 0.08 per unit. And there is another line whose kV rating is 6.6 kV, and it comes out to be and its impedance is given as 0.54 plus this. So we first convert all these impedance, voltages and powers into the per unit value, and then we will formulate the circuit and solve it. We'll first select the base as 12 MVA and 11.8 kV throughout the network. Of course, this will change as per the transformer ratio, but for the time on the generator side, we'll take this as 12 MVA and 11.8 kV. Since this is these XG1 and XG2 are calculated on these two values, so these will not change. XG1 will be same, XG2 will also be same, and since 12 MVA is the base here, this is also on the same base, its XT2 will not also change. It comes out to be, it will remain as it is, 0.12. Now XT2 is 0.08 on its own base, that is 3 MVA. We need to calculate it, recalculate on 12 MVA. So it will be equal to 0.08 into 12 by, that is SB2 by SB1 into VB1 by VB2. Since the voltage here is 11.1 and we have taken this base here, it means the base on this bus will be 33 kV, the base on this is 6.6 kV. The base remains the same, it will not change. Whether it was this value, that is MVA is 3 MVA or 12 MVA, it will remain the same. That's why here it has not shown that voltage value. So XT2 will be equal to 0.32 per amp. Base voltage for line 1, that is this line from here to here, that is 33 kV, which we have discussed just before a few seconds. Base voltage on line 2, that is line 2 is this. It will be definitely 6.6 kV. So what will be the value of Z line per unit, that is this Z multiplied by SB divided by VB square, or it has first calculated this base values, that is ZB line, it will be equal to 30, this V square by 12, so it will be equal to 90.75. ZB line 2 is equal to 6.6 square by 12, it comes out with 3.63. So Z line 1 in per unit will be equal to 9.45, that is this 9.45 plus this divided by 90.75, it comes out to be this value. Similarly, the line impedance of the line second will be equal to its actual value divided by its base value, it comes out to be this. Now this is the circuit, actual circuit. We have replaced this generator by its equivalent circuit, this generator by its equivalent circuit. This is the transformer, this is the transmission line 1, this is another transformer, this is the transmission line 2. And when the fault occurs here, it means it is connected to the ground. And you should always keep in mind that the generators are connected like this. It means this is the positive terminal and this is the negative terminal. And this negative terminal will be itself connected to the ground, since this fault is also between this point and ground. So it means it is connected like this. I hope you understood this circuit, as we have discussed in the first class also, in which we discussed the reactance diagram or impedance diagram. So from here, this is the two generators connected in parallel. After that, these are the different transmission lines and different transformers. And this is the 11.8 kV bus on which we have to calculate the voltage, and this is the fault current which we have to calculate. So we can simply add these transmission line impedances. This is 0.12, 0.32, that is 0.44, 0.13, 0.11, 0.55 plus 0.13 0.36, it comes out to be 0.689. That is, I first calculated the J terms. So the real part will be 0.104 point this, it will be equal to 0.252. So this is the total impedance from point this to this. You can say from bus to from point F. Now we'll first calculate the Thevenin equivalent of this circuit. You can see from here, we are assuming this to be one angle 0 and one angle 0. It is because you can see since the base voltage here we are assuming 11.8 and the rating of the generator is 11.8. So the base value is same and the rating is also same. So it means 11.8 divided by 11.8, it comes out to be 1. And we are assuming both are at the same angle, that is angle 0. We are taking them as a reference. So the circuit will be like this. Now from here we need to first calculate its Thevenin equivalent. When we calculate its Thevenin equivalent, we open it from here and here and then use the circuit analysis. You will see that since this voltage is equal to this voltage in magnitude and angle has same, when we use this any circuit analysis, there will be no current flowing because the voltages are same. They will not allow any voltage current to flow. That means this voltage, so there will be no voltage drop between this impedance and this impedance. That means this voltage will be simply reflected at this voltage, but Thevenin voltage will be, I mean to say, will be here 1 angle 0. That is written by him as like this. And Thevenin impedance will be from this point to this point. We will short them. There will be a parallel combination of these two. That is what it has written over here. This is the Thevenin equivalent of this circuit. It is 1 angle 0 and the parallel combination of these two. It has been separated from this to this because we need to calculate voltage at this point. So when we calculate the equivalent of these two, it comes out to be 12 into 15 into 12. It comes out to be 0.18 divided by 0.27. So it will be total 0.66. This comes out to be 0.66. So it has added to 0.66 to this portion. It comes out to be 0.252 plus J 0.755. Now the fault current will be simply this voltage divided by this impedance, total impedance, that is 1 angle 0 divided by 0.252 plus J 0.755. It comes out to be this value. Base current can be calculated. It will be 12 into 1000 divided by root 3 into 6.6. Actually this is 12 MVA. We can take 1000 from here. It comes out with 12,000 kVA. That K and this K will cancel out and total base current will be like this. So to convert fault current to base actual current, it comes out to be this multiplied by this value. So the fault current will be equal to 1318.4 at an angle of 71.5 amperes. Now this is the fault current. Now we have to calculate voltage at this point. Voltage at this point. The voltage will be nothing but the voltage drop across this total impedance. That voltage drop will be fault current multiplied by this impedance. So that voltage drop will be equal to the fault impedance will be this much, 0.252 and plus J 0.698689, that is written over here. So the total voltage will be 0.1256 at an angle of this, that is the fault current multiplied this impedance, which comes out to be this value. And when we multiply it with the actual base value voltage, it comes out to be this, that is 10.86 at an angle of minus 1.6 degrees kV. This is the voltage at 11 kV bus. So this is actually the same exercise which we have done in the first numerical, but in this case you are asked to find out the voltage. It is found like this. It can be found like this also if you calculate this current by using the current divider rule. If we calculate this current again by using the current divider rule, this voltage can also be equal to this minus this voltage drop, and that voltage drop will be equal to J 0.12 multiplied with this current. Similarly, this can be equal to this minus this voltage drop, that is this minus J 0.15 and the current flowing through this. This can be done, but you have to then write another step for that case to calculate this current and then find out this voltage drop and then subtract that voltage drop from this. But here you already have calculated this impedance multiplied with the fault current, you can get the value of voltage at bus this. We'd like to do one more numerical, that's again simple numerical, in which we have two generators. One is rated 15 MV 11 kV, another 10 MV 11 kV. XG1 is 0.1, XG2 is 0.1 on its own rating, and we have then delta Y transformer 11 by 66 15 MV, XT is 0.6. So it is given like this. The generator is connected to a transformer as shown as this. Calculate the sub-transient current in each generator when the three-phase fault occurs at a high voltage side of the transformer. That is, fault occurs at this. We'll first calculate it as this reactance diagram by choosing the base MVA as 15 and base kVA as 11 kV. I told you the last time that it is advisable to take the base MVA as the highest base. Since highest base is 15 MVA, we can take this as. You can take this also. In that case, there is no harm. But it is advisable to take this as a base. So here also it has taken 15 MVA as the base. So this will not change because this is calculated on this on the same base, that 15 MVA 11 kV. So it will remain as it is. But this will change because this is calculated on 10 MVA base and voltage is same. Since voltage is same, we will not. It has not written the voltages over here. That is 11 by 11 whole square. That is equal to 1. So the xg2 will be equal to xg2 dash will be equal to 0.10 into 15 by 10 because now the SB2 will be 10. It will be equal to 0.15. So subtransient current means we have to calculate this in subtransient period. And also, since it is given that xg1 and xg2, these are the subtransient reactants given, whatever be the current we will get, that will be subtransient current. If it is not given, it is very difficult to get then the subtransient current. So xt is again given on the base of 15 MVA. That is here advantage because there are two values which coincide with 15 MVA, so we don't need to change this also. So the simple circuit reduced to this. You have 1 angle 0 because the voltage rating is 11 kV. So EF we can take as 1 angle 0, 1 angle 0, 1 angle 0. So this is J0.1, J0.15 which we have calculated, and J0.06 which is as it does not change. So similarly, as the previous question we discussed, the Thevenin equivalent will be equal to this voltage source in series with the parallel combination of these two. So it comes out to be like this. So the parallel combination of these two will be equal to 0.06 because 15 into 10 is 150 divided by 25, that's 0.06. 0.06 plus 0.06 is 0.12. It hasn't shown that like this. So the total fault current will be now this V naught divided by 0.12. Since it is 1 angle 0 divided by J0.12, it comes out to be J 8.33 per unit. So when we calculate fault current, we can use the current divider rule to calculate the generator 1 current and generator 2 current. Generator 1 current will be equal to J0.15, that is the current divider rule. This current will be equal to this impedance divided by the summation of impedance multiplied by current. That is, the current through this will be equal to J0.15 divided by the summation of 2, that is J0.1 plus J0.1 into the total fault current, that is this. It comes out to be J5.0. Similarly, Ig2 will be equal to current in this will be equal to this impedance divided by summation of these two impedance multiplied by current. This impedance summation of these two impedance multiplied by this current will be equal to J3.33. You can also calculate it by subtracting this current from this current. This will also be the same. So the base current, we can calculate now the currents in the actual values. Base current will be equal to 15 into 10 divided by root 3 into 11. It comes out to be 787.3 amperes. And Ig1 will be equal to 3.936 kiloamperes. Ig2 will be equal to minus 2.621 kiloamperes. Similarly, IF will be equal to summation of these two, that is 6.557 kiloamperes. So I hope you understood this, how to calculate, how to use the per unit system to calculate the fault current, to calculate the different voltages. If you are asked to find out the voltage over here, you can simply calculate it. If you are asked to find out anything else, you can calculate regarding it is simple circuit analysis. So for the time, I think it is enough. Thank you very much.